Okay, I'm going to start with finding f of g of x. And f of g of x means you're going to take your first function f, and wherever there's an x, you're going to substitute in g of x. So let's go ahead and get our function f ready to substitute into. My f function is 4 over 1 minus 5 times x. And so where there used to be an x next to the 5, I now have parentheses because that's where I am going to substitute in my g of x function. And g of x above is 1 over x. And so in for my x, I'm now going to put 1 over x. So f of x is in red and g of x is in blue, and just got substituted in for the x that was there. And then we're going to clean it up. And I know this is a little bit of a challenge, and there's not only one way to work through this. Mr. Manning has another technique to clean up his fraction, but I'm just going to stick to the basics here. If you want to sneak a peek at his example, I think it was example 3 in our notes, you can look at that and see how he cleans up his fractions. But I'm going to take my 1 and I'm going to write it as a fraction. So I'll write 1 as 1 over 1. And then I'm going to multiply my 5 by the 1 over x. I'll just turn 5 into a fraction by putting it over 1 first, and then fractions get multiplied straight across. You don't need to put the 5 over 1. I just want to show you how things line up when you're multiplying. So the 5 is going to be multiplied straight across by the 1 in the numerator. So then I end up with 5 over x. And then the 1 minus 5 over x has to be combined. So I'm going to find a common denominator between the two fractions, which would be x. I find the common denominator by multiplying both my denominators together, and 1 times x just gives me x. And then 1 times x gave me my new denominator of x, so I also have to multiply my numerator by x as well, and 1 times x is x. And over here, x times 1 gave me x, and then 5 times 1 gives me 5. And now that I have my common denominator, I can combine my fractions down here together. And I'm also going to turn 4 into a fraction by putting it over 1. And then I end up with x minus 5 all over that common denominator of x. Once you get a common denominator with fractions, you can perform the operation on the numerator, whether it's plus or minus, and then put them over one single fraction bar with that common denominator. So that's what I did. And then when you have one fraction divided by another fraction, you change division to multiplication, and you take that second fraction or the bottom fraction and you invert it. So the x will now be in the numerator and the x minus 5 will now be in the denominator. And then I'm going to multiply straight across to get 4x all over x minus 5. And like I said, I know that this is difficult to find a common denominator and to combine your fractions together if you don't know how to do that. So you can sneak a peek at Mr. Manning's video for example 3 in I think 2.3. I'm pretty sure it's example 3, and see how he cleans up his composite function. Now the domain. I am going to be looking at the domain of my composite function, and in my composite function I have a fraction, this big red fraction bar right here. And everything that is underneath that fraction bar, I am going to take that entire expression and I am going to set it equal to 0 to figure out what makes this entire denominator equal to 0. So I have 1 minus 5 over x set equal to 0. And then I'm going to subtract. Actually, I changed my mind. I'm going to add 5 over x to both sides. I get 1 is equal to 5 over x. I'll just add that to both sides. I'll turn 1 into a fraction, not that you have to, but I'm just going to do it anyway and look at this as a proportion, and I'm just going to cross multiply, and x will equal 5. And technically that's what x cannot equal. So that's the first domain restriction that I have. Now I'm not done yet because I need to make sure that I take care of any domain restrictions from my inner function, because as you can see, my inner function g of x has its own fraction. So I need to figure out what makes this little denominator right here equal to 0. So I'm going to take my x that was underneath that fraction bar in g of x. I'm going to set that equal to 0, and I'm going to solve, and it's already solved for. There's nothing to do except realize that that's a domain restriction, what x cannot equal. So the domain of my composite function is in red, and the domain of the inner function is in blue. And together, both of those are the domain restrictions of the whole entire composite function itself. So the domain of f of g is going to be everything but 0 and 5. And on a number line, 0 comes first, 5 comes second. Those are excluded from our domain, but we get everything else. You don't need to draw the graph. I just think it lines everything up nicely and is a good visual if you're not that comfortable with writing your domain interval style. So I'm just going to put it in anyway here. My domain goes from negative infinity up to 0. Then we union that with the middle of the graph, which is from 0 to 5, and then we union that with the right side from 5 to infinity. Okay, so let's go ahead and do g of f. Let's see how that looks. So g of f of x means you are taking your g function and you're substituting in f of x for all of its x's. And I'm going to get g ready to sub into, and g is 1 over x. So I'm going to write 1 over x. That's what g was in red. And then inside, where the x's used to be for g, where I put parentheses, I'm going to put in f of x. And f of x is 4 over 1 minus 5x. And so f of x is in blue. And then I'm just going to clean that up. This is a little bit easier to clean up than the first one. Then f of g. I'm going to take my 1 and turn it into a fraction. And then I end up having a fraction divided by a fraction. And when you have a fraction divided by another fraction, you are going to invert and multiply. So I take my 1 over 1, write it down. I'm going to change division to multiplication, and then I'm going to invert that second fraction, or the bottom fraction. 1 minus 5x goes on top now, and on the bottom, in the denominator, goes the 4. And then when you multiply straight across, you just get 1 minus 5x over 4, because 1 times anything is just itself. And that is done now. And then I'm going to find my domain. And so let's find the domain of the composite function here above. Now I'm going to be looking at my whole entire unsimplified composite function, and I see I have a fraction bar, and so I need to figure out what makes this entire denominator under that red fraction bar equal to 0. And so I'm going to take my 4 over 1 minus 5x and set that equal to 0. And then I'm going to cross multiply, and I'm going to do 4 times 1 to get 4, and then 1 minus 5x times 0 on the other side. and then 1 minus 5x times 0 is just 0, and I get a false statement or equation, and there are no extra restrictions there. So 4 equals 0 does not make sense. It's just a false equation, and therefore there are no like solutions or no domain restrictions for my composite function. So now I have to go and figure out any domain restrictions on my inner function, and I do have a fraction bar on my inner function, and I need to make sure I figure out what makes that denominator on my inner function equal to 0. So my inner function's denominator is 1 minus 5x. I'm going to set that equal to 0. I'm going to add 5x to both sides, and then I'm going to divide by 5, and I get x is equal to 1 over 5. But technically that's what x cannot equal. And my domain of my entire composite function is the domain in red of the composite function itself that you created, plus any domain restrictions from the inner function in blue. And so x cannot equal 1/5. Domain of g of f, you cannot have x equal 1/5. So there's a little hole there. And I'm going to shade in everything else because everything else is included in our domain. And when we write that interval style, we go from negative infinity up to 1/5, and we're going to union that with 1/5 to infinity. And I just want to say one more thing. Make sure when you are finding the domain of your composite function, you're really just looking at the original function that you substituted into before you simplify everything. You do have to simplify everything and clean it up, but when you're finding the domain, you are inspecting the unsimplified function that you first plugged into.